All right, thermodynamics and kinetics. The balance reaction between N2 and H2 is N2 and 3H2 is equal to 2 NH3. As you can see, there's a decrease in the number of moles as the reaction proceeds. Following Le Chatelier's principle, this would cause a decrease in entropy. Because of this, delta S is negative. Given that delta H is negative, the reaction is exothermic. This means the release of the heat into the surroundings would increase the entropy, and therefore delta S of the surroundings would be positive. An exothermic reaction has an inverse relationship between temperature and KEQ. Therefore, increasing the temperature would decrease the KEQ. Relative to Gibbs free energy formula, if KEQ decreases, the negativity of delta G would decrease, i.e. become more positive. This would decrease the spontaneity of the forward reaction. In the top right, you can see the graph with a positive slope and intersecting at negative 92.4. The reaction would proceed forward as the partial pressure of H and N increase. This is because, according to Le Chatelier's principles, as the partial pressure of the reactants increase, the reaction will proceed forward in order to decrease the reactant partial pressure and increase the product pressure in an effort to even out the distribution of pressure. The relative magnitude of the reaction quotient would decrease as the pressure of the reactants increased, and therefore the reaction would proceed forward in an effort to shift Q back to KEQ. As reactant partial pressure is increased, the forward reaction would become more spontaneous, so delta G would be becoming more negative or decreasing.
So in question three, we're more focusing on the catalysts that affect the Haber-Bosch process. And so in question A, it asks us to use the graph to calculate the uncatalyzed activation energy. And for this, we use the equation natural log K equaling to negative EA over R times 1 over T plus natural log of A. And for this, we're just going to use use the slope, which is the M equals negative EA over R, which is our slope for this equation, but it's also where we're going to find our activation energy. So for EA, we use negative 60523, which is our negative slope, times it with our R constant, which is 8.314 joules over mole. And with that, we would get our final value, which would be over in joules over mole. We convert that to kilojoules over mole, which is our 503.188 kilojoules per mole, which is our activation energy with the uncatalyzed constant. Next. And for question three, it focuses in more on how the catalyst speeds up the reaction. So in part one, it asks us the activation energy and its effects by the catalyst. So for question one, it focuses on the types of catalysts used in the Haber-Bosch process, which was heat, high pressure, which also can be used as compression, iron-based, and enzymes called nitrogenase, which is a catalyst of interest stated in the article. All the catalysts serve to speed up the reaction by lowering the activation energy. The heat conditions for to lower the activation energy would be between 300 and 500 Celsius. The conditions for pressure are between 200 and 400 atm to lower activation energy. The enzyme of the nitrogenase acts as a biological catalyst binding to reactant molecules to lower activation energy. The iron-based catalyst forms bonds with the nitrogenase and hydrogen gas, then releases ammonia from the catalyst. And then we see this by the slope of the line would become less steeper because of the lower activation energy. The inverse of temperature, the inverse of K, which is the horizontal axis, would be a larger value. Qualitatively, the features of the graph would be smaller slope and a higher horizontal value on the x-axis, which is our K. And then on to our next question, question four. It talks about, question four talks about, and then question four talks about our calculated reaction quotient for this reaction, in which we would just create a reaction and calculate Q and compare it to our KEQ, which is 4.34 times 10 minus 3. So for this, we do products over reactants to get our Q. We use our given atmospheric values, which were 250, to get 0.0064. And we compare that to our KEQ, which is bigger than our KEQ, which demonstrates that this will proceed spontaneously in the reverse direction to reach equilibrium. This is because Q equaling to 0.0064 is greater than our key EQ, meaning that there's more production of reactants to reach equilibrium. And to our next question in part B, which is where we use an ice table to calculate the partial pressures for nitrogen and hydrogen at equilibrium. So for this, we would set up the equation as normal for nitrogen plus hydrogen, giving us ammonia, and we would use our initial pressures which were 50, 50, and 200, and then our change was in negative x minus 3x and minus 2x, and then our ending, which would be 50 minus x for nitrogen, and then for hydrogen would be 50 minus 3x. And then for our ammonia would be 200 minus 2x equaling 196.3. That is because our final partial pressure for ammonia is 196.3, which was given to us at the beginning of the problem. And so we would find x in that equation, and we would find x equaling to 1.85. And so we would just plug in 1.85 to our ending equations for nitrogen and hydrogen. And by doing that, we get a partial pressure of nitrogen gas equal to 48.15 atm. And we would get a hydrogen partial pressure of 44.45 atm.